So I welcome you, Ben, to this stage and have a nice time.
Excellent. Thank you very much, Paavo, for introducing me, and thank you to Intelligenzia and all the students of cognitive science for inviting me up. I have to remember to hold this here. So I'm a docent of cognitive science, and I came from a background of computer science. So when I do cognitive science, I'm essentially looking at it from an empirical, data-driven perspective. And that's why I want to talk about cognitive science and data, and to sort of get into an issue that I think is implied by the very foundation of cognitive science, and only maybe now in modern times maturing, so it took a good few decades. But the implication is that with the disciplines that cognitive science comes from, making different schools of empirical work or empirical research work together is sort of required to move ahead. And so that's why you have to ask, how many wise blind men does it take to see the elephant? The myth or the story of the wise blind men and the elephant is very old, from the Indian subcontinent, and concerns, well, I can tell you how it was put into words by John Godfrey Sachs in a Victorian poet. He said, "It was 6 men of Indostan, to learning much inclined, who went to see the elephant, though all of them were blind, to see by observation and satisfy his mind." And they go on to examine the elephant, each one observing a different part. One grabs the tail and thinks it's like a rope, and one grabs the tusk and thinks it's like a spear, and one grabs his leg and thinks it's like a tree. And they're all very much convinced of their observations. And this goes on for 6 stanzas, so I don't want to read that. But then Sachs ends by saying, "And so these men of Indostan disputed loud and long, each in his own opinion, exceeding stiff and strong, though each was partly right and all were in the wrong." We come from, coincidentally, 6 disciplines, if you believe this picture from Miller, 2003. It was in a pretty good journal, so I guess we have to. And these 6 disciplines are more or less quite heterogeneous. They're quite different. And they all started off in some way connected in this cognitive revolution. And over time, they all became more or less totally interconnected. Nowadays you have, I mean, this is mainly due to technology, I think, but nowadays you have neuro-everything. You have neurophenomenology, the neuroscience of the subjective experience of a person, if you can believe that. I do some of that, so I think I believe it. But artificial intelligence is also a big driver for this. You have AI everywhere. I come, as I say, from computer science, so my background or my area is maybe mostly to do with AI, and then a little bit of neuroscience over the years and a little bit of psychology over the years. I've even tried to write a philosophy paper with one of the speakers here today, and I've even worked on a linguistics study with a linguist helping me out. So I think it's open for entry. The field of cognitive science is open for entry for anyone, even me. But still you have this sort of issue of collaboration, of how do you get things, how do you get these disciplines to meet together. So I'll talk a little bit about how data is gathered in each case, in order to see maybe where the problem lies, or where one of the problems lies, and maybe give an insight into where we can go forward. So, for example, in philosophy, you deal with thought experiments. This is the trolley problem. Very famous thought experiment where you have to decide, would you direct a speeding trolley towards a single person lying on the track, or a group of people lying on the track. There's many variations of this. It might be that the trolley is already going to go one way and you only have the choice of whether to divert it or not. And you can have different concepts of how this applies to society, and then other people will pick up your concept and debate it, and this is how philosophy does data gathering. It's basically a debate format. So you have a sample size of one, the person that you're arguing with, or maybe the order of samples is in the ones. It can be probably not more than that. It's also sort of interesting that with AI you're going to get interesting philosophical problems becoming reality, where now some AI is making the decision of which way to drive the trolley in the case of autonomous vehicles. But that's maybe just a single case. Anthropology, you have to go and get the data by observation. It's not just Native American people, of course, that's the poster child for anthropology, but you can go and look at German craftspeople or what have you. But the point is that you have to go and get data by observation, and it becomes a very qualitative process. So highly different to, for example, neuroscience, where your data comes from very empirical methods of observation. It's like a hard science, really. This is a picture of the skull of Phineas Gage, one of the most famous case studies in neuroscience. And neuroscience originated with case studies and lesion studies, studies of damage to the brain, which can show you something about the behavior, a change of behavior that that brain region relates to. But then moving on to modern times, they've even managed to reconstruct a simulation of what the damage to this guy's brain might have done. So he got a steel shaft through the head in a railway building accident, 19th century, and he survived, and his behavior changed, and from this observations many inferences were drawn. And now they've even gone so far as to simulate what may have happened to his brain. So we're dealing much more in a world of high data density, and case studies are maybe the basis for that, but perhaps gone beyond. Psychology, so you're asking self-reports a lot. I'm talking mainly about the canonical ways of gathering data. There are, of course, a lot of ways of gathering data, but you have self-report, a person describes how they feel, or some kind of a response test. Person responds to a particular task, and then you infer something. This is a task of testing executive function called the Wisconsin card sorting task, where you have to match the test card to one of the displayed matching cards based on a rule which you don't know. And you try to figure out whether it's right or wrong by trial and error. You get told every time whether you're correct or not. So it's a test of executive functions, and this kind of response data is obviously not as high density as the neuroscience data, although you might have the same number of individuals being tested, or you might have a lot, like an order of magnitude more people being tested with self-reports. And then artificial intelligence. Talking about data gathering, we all know that when you use a free online service, the reason it's free is because the data is going to the service provider. So your Facebook and your Google is all basically, you pay with your data. This is a different illustration. This is an illustration of a mechanical Turk, Kellerman's, or Keppelin's, sorry, von Keppelin's chess engine. the idea is that it was a machine that was supposed to be able to play chess with you again, 19th century, but in fact the hidden trick is that there's a person inside playing the chess machine. This is actually how a lot of AI data is gathered. Amazon.com has a service called Mechanical Turk, where individuals provide you with some little bit of knowledge work. So they make a decision for you. And so the data comes from a lot of AI. It's artificial intelligence, and I'm not saying that the intelligence it displays is in fact a guy behind the curtain pulling the levers, but it's still built on human decisions, a large aggregation of human decisions. It's scaling of human decisions. So AI, your sample size is in the millions, potentially. So how do you get from a sample size in the millions to a sample size of 1 or 2? How do you compare those pieces of data? It's an issue. You have these scaling issues. This is an illustration from the Human Brain Project. This is a slightly different related problem about how scale affects cognitive science. But even within, so this is a within discipline problem, but even across disciplines you have a similar problem of scaling of the amount of data that you're dealing with, and the compatibility of the data, qualitative, quantitative. Did you get it by asking a person how they feel, or did you get it by observing something about their neurotransmitter levels, for example? So now I want to switch tack a little bit, so that's the problem. And I want to provide an example of a study, a little small study from the cognitive science experiment lab course last year. It's a pilot study, and it illustrates, again, the problem, but exemplifies it, and then we can see maybe where an answer might lie. The answer only lies out there, hasn't been kind of implemented yet, but the study was about flow experience, so we wanted to examine this experience of feeling like you're in the zone, of doing something with high skill that has a high level of challenge, doing really well at it, and feeling like you're in the zone. So this theory is developed by this guy called Csikszentmihalyi a long time ago, and it's become sort of a popular psychological theory, if you will. And yet there is underlying it a core of kind of a good cognitive science questions, like what are the kind of neurological states that could allow you to enter this experiential state? How do you match your challenges to your skills over time? How do you learn? So we wanted to examine this, and we had this excellent test game lying around. This is a steering task where individuals steer with the steering wheel a cube that flies down the track. It goes faster and faster as long as they're not hitting anything. So there's obstacles all the way down the track, and if you hit one, you slow down, and if you don't, you keep speeding up. And the learning of this game sort of leads into a state of becoming in flow as you try to manage this very sort of autonomically or automatically challenge skill matching task. So if you're not good enough, you hit something and the speed drops down, so the challenge reduces. If you're very good, you don't hit anything and the speed increases. So it's always keeping you in this zone of flow, or that's the intention. And we're going over time. And so we aim to study flow with this task. People came in and they played the game over 8 consecutive days, and they they rated themselves. They played 5 times a day, and they rated themselves on this flow scale every time they played. So we know how their learning improved and how they felt afterwards. And we plot that on a learning curve graph, which is basically showing, barely see this, so showing the duration of their run against the number of runs. So as they increase the number of runs, they decrease their amount of time it takes them. So they're learning. And this is plotted in a log axis. That means that you take the logarithm of the values, which allows you to get a straight line where the real data or the pre-transformed data would show you this kind of curve. And when you fit the straight line, the whole data set looks quite nice. This is individual subjects in each box. The data set looks quite nice, and they're all kind of learning, and it's nice. And I won't go into the flow, but it looks like the flow is good because they have higher flow scores when they're doing better, as in getting lower lap times. But what I want to point out with this is basically this one subject here. If we look at this kind of curve that goes across the linear data, the non-log transformed data, we see that it goes back up again. It's not a good way to plot learning, a good theoretical way to plot learning, but it allows you to look for a plateau in the data, in the learning data. Where do they kind of start failing to improve? And yeah, this one is doing it early enough that you can think that maybe they stopped trying. And it indeed feels like they stopped trying from all of the data that we had, including the flow reports and so on. And we don't know why they stopped trying from that data. So we just asked, well, I mean, there were students doing the research who knew the individual, and we asked them, and they said that they didn't care. So we got that data point because we had a kind of observational anthropological connection. And the question is, with just 9 subjects in the study, it's not really a groundbreaking study. It's not really going to get you into, I mean, get you on the news. So how do you scale that up? How do you scale up this human observation? How do you make it robust that you find these things in your data when they occur? Otherwise, it's just noise. If you can't explain it, it's just noise, and it doesn't help you. So the end point is the reason why I didn't explain how linguistics gets their data is because maybe the answer lies in this discipline known as informatics. Lots of other disciplines have this. There's bioinformatics, there's medical informatics, there's all sorts of informatics. And maybe the answer lies in having a sort of semantic structure that ties together all of your data and allows you to know that this data point relates to these other data points, and build a structure out of that allows you to get these results at scale. This is the visualization graph of databases in the linked open data standard, and these green ones are all the linguistics databases. So they've already gone ahead and done this. Neuroinformatics is bringing this on for neuroscience, and the rest of us need to get ahead and do it as well. Basically, that's what digital humanities is about, I guess. Maybe I should let the professor of digital humanities tell what that's about, but that's, in my opinion, where we're going is linked open data, and how many men, wise blind men or women, does it take to see the elephant? Maybe all of them. Maybe you need to link everything together before you start to get answers at scale that are robust and give you sort of an insight into the human mind and human thinking, because it's not very easy. All right, this is me doing experimental work. Thank you very much.
Thank you, Ben. Now we have some time for questions. If there are well, any questions you like to ask from Ben, from any subject, or any subject. Okay. We'll bring you a microphone right there.
Okay, so I have a question about the flow study. Like my everyday idea of flow has always been like there's always some like you really like what you're doing. So like how about those people that you studied that didn't like games at all? Is like how can you like measure flow in that?
One of them was the blue dots. One of them was the one who didn't care and stopped trying. They hit some kind of a well, I mean, the task starts off relatively easy, and they hit that threshold, and after that, they weren't going to keep putting the effort in. And yeah, it's good to have those data points. It's good to have those people in the sample, because usually when you do a study like this, you're getting a self-selection bias. People are coming to your study who want to be there. We got these people, we got a couple of people who were there just because of their friends were doing the study. There were students doing the study and they got their friends in. And that's why we sort of know a little bit extra about those, and that's what happens, I guess. You can't force flow, and I guess you can't force any higher cognition, or at least very high level cognition, because it all depends on this intrinsic motivation issue. So I guess it presents a problem for studying those things if you think about it that way, or else it's an opportunity to study the difference between those who do and those who don't.
Does this work? Yeah. Did you line me a line? All right. I'm just going to talk. Did you have some kind of measure of fatigue, or like the basal fatigue or susceptibility to fatigue during the course of the experiment?
No, I don't think so. No. Not that I remember. Okay. I did that in another study. Yeah, I mean, it's always a good idea if it's a kind of really meaningful factor. And I suppose if this was a study at scale and we didn't have that kind of ability to ask the individuals, so if we put this game to them in a more scaled format, like an online format, then of course we'd need to ask that kind of thing. Here I think we were relying a little bit on this kind of personal observation thing.
Okay, thank you.
Okay, thank you for the questions, and